All right, now we're going over chapter 6. So learn more about the physiology of the cell and cell membrane. Okay. All right. So we touched a little bit upon this stuff earlier. The extracellular environment versus the intracellular environment. Okay. So you have the cell, and then you have everything outside the cell. Okay. So the extracellular environment includes everything outside the cell. So the cells receive nourishment from the extracellular environment. It releases waste into the extracellular environment. They communicate with each other through hormones and stuff in the extracellular environment. Okay. So the fluids. Okay. So 67% of water is in the intercellular compartments. Okay, 33% is the extracellular compartment. Out of that 100%, okay, out of that 33%, okay, 20% of that is plasma. Okay, and 80% of it is the extracellular fluid or the tissue fluid. Okay, or the interstitial fluid. Okay. Okay. It should be called interstitial fluid, not extracellular fluid. I screwed that up. Okay. So plasma, interstitial fluid, okay, intracellular fluid. Okay. Okay. The extracellular matrix. The extracellular matrix contains protein fibers of collagen, elastin, and gel-like ground substance. Okay. The protein fibers provide structural support, and different amounts of collagen and elastin provides different amounts of structural support for whatever you're looking at. Okay. The ground substance is made of glycoproteins, okay, proteoglycans, and integrins. Integrins are glycoproteins that extend from the cell cytoskeleton and bind to the extracellular matrix. Okay, so the functions of integrins impart a polarity to the cell. So the top surface and the bottom surface are going to be different. Okay, they affect adhesion and motility and affect proliferation of cells. Okay, the plasma membrane, I'm sure you guys heard this terminology before, that the plasma membrane is selectively permeable. Okay, all right. By selectively permeable, it means some molecules can cross but not others. Okay, so it is generally not permeable to protein, nucleic acids, or other large molecules. Okay, so you have a phospholipid bilayer. That phospholipid bilayer outside is hydrophilic, okay, and the inside membrane part is hydrophobic, but in the middle is this hydrophobic core. Okay, so small uncharged molecules can move very easily through it. Okay, fats and stuff can move really easily through it. Charged particles, okay, ions, cannot. Okay, water sort of can. It's not great at it, but it can, and it gets in and out because there's simply so much water that some of it can move in and out. Okay, and even though water is slightly polar, it's small enough that it can maneuver itself in and out. Although it does use something called aquaporing to speed up that process. Okay. All right. Types of transport. Non-mediated transport. Okay, this is usually known as simple diffusion. Okay, simple diffusion of ions through non-specific channels. Okay, simple diffusion of water, which is also known as osmosis. And we'll talk a lot more about osmosis in a little bit. Okay, the carrier-mediated facilitated diffusion, where things are specific, they go through specific pores, and active transport. Okay, so cells are lazy. Okay, so passive transport, molecules move from higher to lower concentration without using any energy. Okay, if it's higher on one side and lower on the other, and that's go naturally go by itself, you're not going to spend ATP to make it, to do that. Active transport, you are. Okay, active transport, you go from lower to higher concentration, so you actively have to pump it. Okay. 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 Let's go through a couple of definitions first. Solution consists of a solvent and a solute. Okay. The molecules in a solution are in a constant state of motion. Okay. Okay. So if you have a cup of water, okay, if I dump salt on it, salt will first accumulate where you dumped it, right, the bottom of the glass. But there's always motion. The fluid is always moving and circling around. Okay? And eventually what will happen is the salt will become distributed uniformly throughout the solution because that has to obey the second law of thermodynamics. Okay? The more randomness, the better. So the diffusion increases the entropy. Okay? Okay. So if I dump salt onto this side, okay, salt will eventually move to that side, okay, until they're equal. And then the random movement cancel each other out. Just as many salt particles move to the right as move to the left. Okay. All right. Mean diffusion time. Okay. One of the reasons why cells are small, okay, and you can't have very large cells, is this concept of diffusion time. It takes time. If I drop things here, it takes time for the random movements to bring it over here. Okay? So, and time matters to the cell. Okay? So, the mean diffusion time, the average time it takes the cell to diffuse, okay, it increases with the square of the distance the solute must travel. So if you double the distance, okay, you increase the time that it takes 4 times, fourfold the time. Okay, so if it takes 1 minute to diffuse from like 1 inch or 1 centimeter, then it will take 2 minutes to diffuse 2 centimeters. It will take 4 minutes to get to 2 centimeters. It will take 16 minutes to get to 4 centimeters. So that increases dramatically. That's why the smaller the cell, the faster things diffuse across. Okay, that's exponentially speed. Okay? So in distance above 100 microns, diffusion time is too long to be effective. So that's why cells are small. Okay. Okay, now we have this concept of a membrane, okay, a semi-permeable membrane. Okay, so this is probably one of the labs, the virtual labs that I'll have you do. Okay, so here is the dialysis membrane. The dialysis membrane allows certain things through. Okay, so you can see it allows the green things through. It allows the yellow balls through, but it does not allow the purples through. okay? So glucose and small diffusible molecules and ions, okay, can go through. Bigger things like proteins or starches cannot. Okay, okay, through our plasma membrane, small nonpolar lipid-soluble molecules pass easily through. Okay, so examples: oxygen, carbon dioxide, steroid hormones. Okay, okay. Water can pass through special channels called aquaporins. Okay, in a process called osmosis. So here, okay. So carbon dioxide out, CO2 in. Okay, charged ions can pass through ion channels that cross the plasma membrane that may always be open or gated. And we'll talk about the difference between always open and gated in a little bit, but the difference is really what it sounds like. Okay, so large polar molecules cannot pass through the membrane by simple diffusion, but can get carried across through special carrier proteins. Show you that in a little bit. Okay, so here you have a gated channel. Okay, so there's a gate, now it's closed, now it's open. So it goes through the open channel, so I can control how much of these opening balls I take in by opening and closing the gates. Okay. All right, the rate of diffusion is measured by the number of diffusing particles per unit time. It depends on the magnitude of the concentration difference. Okay, so if I create a huge difference, if I drop like pure ink on one side, okay, that will initially diffuse very quickly. Okay, because there's a huge concentration difference in that corner. Okay, also depends on the permeability of the membrane to the molecules. Okay, the temperature of the solution. The temperature, what is actually how fast things are moving. Okay, so the higher the temperature, the faster the molecules are moving around, the faster you get diffusion. Okay, the surface area of the membrane. Okay, the more surface area, the faster things can go from one side to the other. Okay, the more interaction surface, the faster things can move across. That's why cells that are designed for absorption have microvilli. Microvilli dramatically increases the surface area. Okay. All right. Here, this is more accurate than what they said earlier. Okay. Water molecules don't carry a charge. Okay. So they pass through the membrane slowly, but they're polar, so they're not great at it. Okay. This type of diffusion is unique because we're talking about the diffusion of the solvent instead of the solute. That is called osmosis. Okay. Osmosis is in physiology is the diffusion of water. In other, if you get organic chemical stuff, it's actually diffusion of solvent. But really, for all intents and purposes, osmosis is the diffusion of water. Okay. 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 So the requirements of osmosis, there must be a solute concentration that is different on either side of the membrane. Okay. The membrane must be impermeable to the solute. Okay. Or else the solute will move across and not the solvent. Okay. So the only way I can get osmosis to work is to create a membrane that's permeable to water, but not permeable to the solute. Okay, and that way I can control which way water goes. Okay. All right. So here is now my semi-permeable membrane. See how the holes are too big, or the holes are too small for the big purple dots to pass? So now I have more purple dots, okay? The water, the solution, wants to set equal concentration on either side, okay? So water will keep rushing across the membrane until the concentration of water on this side is equal to the concentration of water on that side. Okay. Okay, so the net movement of water is from the side with more water, okay, to the side with less water. Okay. Okay. However, what osmosis is, that's when you say the water moves from the area of low solute concentration to the area of high solute concentration. Okay. Water moves toward the side with a higher solute concentration. Okay. You can talk about any of this way, you just have to understand which way the fluid is moving. Okay. Okay. So there is much more concentration of glucose inside this ball than outside this ball. Okay, so now water will come rushing into this ball. Okay, and that will expand the sac. Okay, now the sac, okay, is when water enters, it's pushing pressure on the sac. The sac is pushing back. Okay, the sac, the membrane doesn't want to expand, right? It wants to go back to its original size. So it's putting pressure back on the water here to leave. Okay, and that is osmotic pressure. Okay, so these two things fight against each other. The pressure generated by the sac on the water, and the water that's trying to rush in to fill in the salt concentration difference or the sugar concentration difference. Okay. Okay. The osmotic pressure is the force, okay, surrounding a cell required to stop osmosis. Okay. If I put the cell in a little iron cage, for example, right? Water can try to rush in, but the cell can't expand into the iron. Like it doesn't work. So water has to stay out. Okay, that's osmotic pressure. Okay, higher solid concentration will require a higher osmotic pressure. Okay, to maintain. So the higher solute concentration, the more desperate the water is to drive in, and therefore the more pressure it puts on the cell membrane, or dialysis membrane in this case. Okay, pure water has an osmotic pressure of 0. So if the inside of this ball was just pure water, then water can only go one direction, leave, and not come in. So there's no osmotic pressure to pure water. Okay. So okay. Okay. So you can see that the pressure here, okay, So water comes rushing in, water comes rushing in. Okay, and you can see like the pressure, right? Can be monitored here. If I put pressure on the membrane, then the water can't come rushing in. Okay. And here I have to put more pressure because there's more sugar here. Okay, I have to put more pressure on it to prevent water from rushing in. Okay. All right. Molarity and molality. Okay. A mole, okay, is 6.022 times 10 to the 23rd molecules. That will always be ingrained into my memory, scarred into my memory anyway. Thanks to my chemistry teacher. A mole is a compound that can be measured in molecular weight in grams. Okay, so the number of atoms in a mole is always 6.022 times 10 to the 23rd. Actually, no. The number of molecules in a mole is the same, not the number of atoms. Okay. So with that, I can make 1 molar solutions or 1 molal solutions. Okay. And these are 2 different things. And even graduate students in biology screw them up. Okay, so molarity is moles solute per liter solution. Okay, so here, okay. It's easier to understand it this way. Okay, so if I was making a 1 molar solution, I would add 1 mole of glucose and then fill it up until it reaches exactly 1 liter. Okay, so I have 1 mole dissolved in 1 liter. Okay, a molal of solution, I take 1 mole and dissolve it. I add 1 liter of water. The total volume of that will be a little bit over 1 liter. Okay, so these are 2 different concepts. Okay. Okay. Osmolarity, okay, or osmolality is the total molality of the solution when you combine all the molecules within it. Okay. So 2 molar solution, 2 molal solution, glucose solution, and 1 molal glucose and 1 molal fructose will have the same osmolarity. Okay, both of these are 2. Okay. So here, okay, this is 2 molal, this is 2 molal. So these 2, okay, will have the same osmotic pressure. So the water will not go anywhere. Okay. All right. So osmolality, okay, the electrolytes that dissociate in water have to be assessed differently because so you take salt, you take rock salt, you put it in water, the salt will dissociate. Okay, all of the sodium will break off from all of the chloride. Okay, this is not true for everything, but for salt, it's absolutely true. All the sodium and all the chloride will separate. Okay. Like in organic chemistry and physical chemistry. There's different compounds that separate some, but not all, and you have to calculate all that crap. That doesn't apply to physiology. Okay, so salt, okay, completely dissociates. Yeah. Yeah, so Stanbridge asked me to teach a chemistry class. I'm like, nope, not doing that. Not to you guys. All right, so salt associates into sodium and chloride and water and must be counted as separate particles. Okay, therefore, a 1 mole sodium chloride solution, okay, would actually be a 2 osmolar solution, okay, because they completely dissociate from one another. Okay. Okay, the osmolality can be measured by freezing point depression. How much the freezing point is lower depending on the number of particles that are present in the solution. The more salt you add to a solution, the harder it is to freeze. Okay, that's why icebergs and stuff are almost pure water. Okay. Okay. So here is glucose. Okay, 1 mole glucose. Because glucose doesn't dissociate, okay, it's just 1.0 osmolality. The chloride is also 1.0 mole, but because they dissociate, the pressure is greater. So it's 2.0 osmolarity. So that means the water will rush out of the glucose solution. Okay, there's more solutes here outside than inside. Okay, so okay, plasma has the same osmolarity as 0.3 molar glucose, or mole glucose, or 0.15 mole sodium chloride. Okay, these solutions are considered isoosmotic to plasma. Okay, so the way we make saline, okay, 0.9 grams sodium chloride, 100 ml water. Okay. All right. Okay. Um, so, or 5% dextrose, etc. Okay. They equal the same amount. Okay. Acidity is the effect of solid concentration on the osmosis of water. Okay. All right. So isotonic means iso means equal. Okay. So if I take a membrane and I separate 0.3 molar solution of glucose and 0.15 sodium chloride solution, there'll be no net movement. Okay. Because again, this dissociates completely, the NaCl dissociates completely, the sugar does not dissociate at all. Okay. Okay, tonicity takes into account the permeability of the membrane to solute, so the solutes can cross the membrane, the tonicity will change. Okay, so if I place red blood cells in a 0.3 mole solution of urea, it will not be isotonic. The urea can actually cross into the red blood cell and actually draw water in with it. Okay, and therefore it will burst. Okay. Okay. the solutions with a lower solute concentration in the cell are hypoosmotic and hypotonic. Okay. Okay. So lower concentration of salt. Okay. Will pull water into the cell. Okay. So you will put. So there's more salt on the inside, so water from the outside will rush in, okay, into the cell and compensate. That will actually eventually burst the cell, okay? Solutions with a higher solid concentration in the cell are hyperosmotic and hypertonic, okay? It will pull the water out of the cell and the cell will shrivel up and crintonate. Okay. So this is why salt is a good preservative, okay? If I make a very hyperosmotic solution, any type of bacteria lands in the solution, all the water will run out of the bacteria and the bacteria will die, okay? So if you want to see this firsthand, take salt, dump it on a snail dies. Cruel, but anyway, it works, okay? All right. Okay. So we must constantly measure the amount of salt in our fluids, okay? Or neurons will be damaged. But you'll understand why in a chapter or two. Okay. The osmolar receptors in the hypothalamus detect changes, increases, okay, in osmolality due to dehydration. This triggers our thirst response. Okay. We compensate that by also the decreased excretion of water through the release of ADH, which is also known as vasopressin. Okay, ADH literally means anti-diuretic hormone. Okay, a diuretic is something that makes you pee a lot, so anti-diuretic prevents you from peeing. Okay, this is also known as vasopressin. Okay, vasopressin, vasovasculature, pressin pressure. It increases blood pressure. Okay, so by not making as much urine, the pressure, the volume of fluid goes back into our bloodstream and increases blood pressure. Okay, that lowers the plasma osmolality, which then sets it back to normal. So negative feedback. Okay. All right. So when we trigger these osmolar receptors in the hypothalamus, thirst makes us drink water. ADH secretion helps us retain water. So water uptake, water retention brings us back to normal. All right, so we'll stop right here for part 1. I'll see you for part 2.